Okay, we're on strand 11, which is talking about the energy associated with chemical reactions. We did 11A. I'm going to jump to 11C because it makes more sense to me to put it in this order. And 11C says we're going to classify reactions as endothermic or exothermic. Using thermochemical equations or graphical analysis. And when we say graphical analysis, we mean, hey, look at the graph and analyze that. Let's see what the graph is telling us. Okay, so thermochemical equations. The first thing you need to know, thermo, you guys know thermo means heat. These are chemical reactions that include an amount of energy with them. So you won't have, just H2 plus O2 produces H2O. You're going to have plus, H2 plus O2 produces or yields H2O plus 332 kilojoules or joules or something along those lines. So it will incorporate an amount of energy with it. And remember, energy is measured in joules. So chemical reactions that include the amount of energy released or absorbed. And remember, I'm saying a chemical reaction, but again, it could be melting or boiling or freezing or anything like that. So there are two main types, as we set up here in the T here, exothermic and endothermic. And we're going to draw some graphs, so I'm going to bring it right over here. And the first one is exothermic. Exo like exit, it means to give off. So this is energy, or specifically heat, given off. So in this type of reaction, it's releasing heat. It's getting rid of heat. Sometimes, now this is not the best way to do it, but sometimes it feels hot to the touch. Now I say that sometimes you can do that because, really your hand is not the best indicator of whether or not something's hot or cold. My hands are always cold. So every time I touch something, ooh, it feels warm, So it's not really the greatest indicator. Get a thermometer. That's the tool we use to measure that. In this case, when we talk about this, the reactants have more energy than the products. And here's where I'm showing that, I'm throwing that delta H in here. We have a negative delta H. I'm going to make those a little bigger so they don't look like a negative sign. I have a negative delta H, which means that, shh, hey, hush, which means that heat or energy is leaving the system. And the system is just the reaction. What this means is delta H, and we can calculate this. Delta H is always the energy of the products minus the energy of reactants. So I'm going to put delta H is equal to the summation of the change in the energy, delta H of the products, minus the summation of delta H of the reactants. Okay, that funky looking E is a summation sign, which just means add that crap up. Okay, so it looks ugly, but it's not bad at all. So here is an equation for this. All right, over here on the side, I'm going to make a graph over here. Doesn't have to be perfect over here. Let's make a graph over here. And on the y-axis, I'm going to put energy. Usually, again, energy's in joules or kilojoules. And on the x-axis, this is going to be the reaction is proceeding. So the reaction is just going along its merry way. So products, reactants over here to products over here. So what I'm going to do is I'm going to make my graph here, and I'm going to move it up here, and then it's going to drop down to here. Okay? And I'm going to get a different pen just so it's a little bit easier to kind of see that things are going on here. Here would be, right here would be where my reactants are. They're right up here. Down here would be where the products are. Products down here. As you see, what I need, in order for this reaction to happen, if it were all downhill, that means this reaction would just, bam, would just go. I wouldn't even have to do anything to it. It would be so unstable that just putting the chemicals out there, it's like, boom, it's going to happen, be careful. What this shows by going up right here is that I need to give it a kickstart. I need to give it a little bit of energy to get it going, and then once it gets that certain amount of energy to get going, boom, now it's going to go on its own. So here are the reactants, here are the products. Notice that the energy is high for the reactants, and then over here for the products, it's a lot lower here. So we have our energy is changing. Where did that energy go? Well, it left. So we're going to label some things here, and I'm going to put a little dashed line right here, and then the one I'm putting a dashed line right here. Okay? This piece right here, from the top of this little piece to the first dotted line, that's called the activation energy. How much energy do I have to give it to get it started? And a lot of times they abbreviate it as capital E with a little bitty subscript A, activation energy. And then from here down to here, this is from actually the reactants to the products, this is called delta H, the change in energy or the change in enthalpy. Enthalpy is the heat. Heat is just a specific type of energy here. My word doesn't show up very well, does it? Okay, so we have some things labeled right here. Here we have our change in energy, and that's what we're really looking for. Here's the activation energy. If it's we're gonna put a little bit into it to get started, and then it's gonna go. It's kind of like when you strike a match. When you strike that match, that friction of the match head against the little thing, I don't know what that thing is called, that little black thing, that friction, that's an amount of energy. You're moving it along, you're giving it a little bit of energy. It increases the temperature, and that causes it to light up. Or even, and I'm going to go ahead and go with the burning thing, if you take a piece of paper, when you put the match to it, it doesn't just immediately burst into flame. You have to get that paper hot enough. You have to give it a little bit of energy first before it really starts catching on and reacting here. So we've got that activation energy. This whole entire reaction, this whole entire graph is exothermic. When the graph looks like this, we have an exothermic reaction. In this case, the reactants have more energy than the products. And when I go back up to this little equation right here, if this number is greater right here, so it's kind of like, oh, 10 minus 12 is going to be a negative number, right? 10 minus 12 is negative 2. What that means here is when you have an exothermic reaction, the enthalpy is negative. Negative delta H. Negative energy. It's not that you have negative heat. What this negative thing means is that the energy, that heat, is leaving the chemicals that you have here. It's no longer bound up in the bonds in here, it's left. And so now we have something that started out with a much higher amount of energy. Higher amount of energy means it's going to be more unstable, and we ended up with something that's much more stable, something that has a lesser amount of energy packed into it. Okay, I'm going to put another little line here. Now we did exothermic. Let's look at endothermic. So when we talk about exothermic, exo, exit, the heat's leaving. And the next one is endothermic, and endothermic is a little stranger. Endothermic means that the energy or the heat is absorbed. This can feel cold to the touch, but again, that's not, touching it is not the best way to do this. So it can feel cold to the touch. Again, your best bet is to get a thermometer and see, well, how much did the temperature change? Did it change by 1 degree, 2 degrees? Did it change by 15 degrees? What's going on here with that? So endothermic, it can feel cold to the touch. The products have more energy than the reactants. And we have a positive delta H, which means that the heat or the energy is gained by the system or the reaction. When I say system, what I mean is, hey, if we have this whole chemical reaction going inside a closed area, that's called the system. And then all the environment around it would be outside of that system. Now, that energy can be transferred into and out of the system. You can put energy into it, you can take energy out of it, whatever is the case here. So now I'm going to go over here to the side, and again I'm going to make my new graph over here. And I'm going to label it the same as I did up here. The y-axis is energy, and the x-axis is the reaction proceeding off to the right. So it's just how we would normally write it when we write down a chemical reaction. H2 plus O2 produces H2O. Okay, so in this case, my reactants are going to start down here. So here are my reactants, and let me get a different pen, and hopefully my pen's going to work right. Here are my reactants, and here are my products up here. My line kind of slanted down here. So here are my reactants and my products. And I'm going to make that line again, just like I did on the top one, where I'm going to take my reactants and go across this way. And I'm going to take my crooked line here for the products. And I'm going to make it back this way. So remember, our energy is measured in joules. If I go from the product line to the reactant line, there's my delta H. And delta H in this case, since my system gained energy, my delta H is actually going to be positive. Again, delta H is enthalpy, heat associated with a chemical reaction. And then here, this line right here is my activation energy. I'm not going to write it out again because all you have to do is look up here and see that EA is activation energy. It takes a lot of energy to get it going. That means that once you start this reaction, if you stop adding energy to it, it's going to quit. So if I take that match and put it to the piece of paper, it's going to take a few seconds for it to light. But then once it goes, I can take my hands off of it. I don't have to keep holding the flame to it. It's going to go on its own. That's an exothermic reaction that is spontaneous. Okay? I give it a kickstart, but then it's going to go. Most of your endothermic reactions are not necessarily spontaneous. It means, hey, they're not going to go on their own. Now, it's not 100% that way, but many of them are. Most of these, when you have a graph that looks like this, we have to keep giving it energy the whole entire time to keep it going. So here's our activation energy. Here is the actual delta H, the energy associated with the chemical reaction. The products have more energy than the reactants did. So this one is an endothermic reaction. So you have two differences here. We have a graph that's for the exothermic, where look at your products. The products have less energy than the reactants. They gave up the energy. They gave it out. It's exited. And then we have the endothermic, where we actually put energy into it. The products have more energy. Where did the energy come from? Well, we had to get it from somewhere. It came from the system outside of it. So endo, we put heat into it, energy into it. So our products are higher in energy than our reactants. So this is what it means when it talks about the graphical analysis. We look at these graphs and we analyze these. The other part is the thermochemical equations, and we'll do that next.